So in the previous videos, we looked at some examples of infinite sums of rectangles or areas of rectangles. We talked about a couple of applications where this would be useful to do. And so, and you'll find in your studies that the integral, along with the derivative, um, are the heart and soul of calculus and are used over and over again. So without further ado, we'll define what an integral is. So let's let f be a continuous function. And this is key. We've got to have a continuous function. In Calculus 2, you'll develop tools for how to deal with the integral of functions that are not continuous on its domain. But for our purposes here, we will say that f is a continuous function on some interval ab. And we're going to consider this infinitesimal dx, which is the length of the interval, b minus a, divided by h, where h is some positive infinite integer. Then the definite integral of f from a to b with respect to dx is defined as the standard part of the infinite Riemann sum. In other words, and this is the symbol we use, this integral is to give you this, it's like a stretched out S, if you will, to remind you that integrals are sums. And so this is the integral from a to b of f of x with respect to dx. And it's equal to the standard part of this infinite sum where we evaluate the function. Well, we, just like we did in the other examples, we'll start at the endpoint, or the left endpoint, and add incrementally values of dx. Also, we'll just say that if we have the integral from a to a, so there is no interval, it's just a point, that integral will be 0. And also a very useful fact that if we change the bounds of integration, then it introduces a negative sign, right? So the integral from b to a of f of x dx is equal to negative the integral from a to b f of x dx. So if I switch the order of integration from b to a as opposed to a to b, it would be a negative. All right, so let's estimate some integrals. We're not going to do it going to the infinitesimals, and that would be an exercise maybe we do in class, but not something you're going to be asked to do by hand. It's a very difficult process, and 9 times out of 10 would take some very advanced mathematics to even compute. But nonetheless, we can still estimate values. So let's use dx to be 1 over 10 to estimate the integral from negative 1 to 1, 2x squared dx. Well, to do this, then we've got to figure out. So let's go back. What are the things we're going to need to know? So we've got our function. Our function is f of x is 2x squared. We've got our dx, but we need to, in this sum, we need to figure out, well, what's our upper limit? In this case, it's not going to be infinite, but we do need to know how many pieces we're going to add. And we also need to know how to define our input values. So the relationship, if you recall, that dx is equal to b minus a divided by, in the definition, it's an infinite integer, but we're going to be finite now, so I'll just call it n. And in our problem, this is 1 over 10. And we know what b and a are. B is up here. This is b, our upper bound, and a is here. So this is equal to 1 minus 1 over n, which is 2 over n. So then if we want to solve for n, we've got an equation here. This tells us that n has got to be 20. And so then our integral from -1 to 1 of 2x squared dx is approximately the sum I equals 1 to 20. Okay, so I need to know what my inputs are. I forgot to calculate that. So what is our xi? Well, our xi, again, let's scroll up to our definition. It is a plus I times dx. So it's going to equal a, which is -1, plus I times dx, which is 1/10. So I over 10. Right? So that's um, our equation, and so we can put that into here. So this is going to be 2 times -1 plus I over 10 quantity squared times dx, which is 1 over 10, which is equal to, well, I sure as heck don't want to add up, run I equals 1 to 20 in here, square it, multiply by 2, multiply by 1/10, and add it all up. That sounds like a horrible activity by hand, but as we observed in the second video, that we can use a spreadsheet to run our calculations here. So let me open up that spreadsheet and enter in the necessary information. So the length of the interval is 2. Our dx is 1/10. Now our x values, remember we're starting at -1 and adding increments of dx. So this would be -1 plus, so I need to put an equal sign, equals -1 plus this value. That would be their first occurrence. And then we're going to add on to that. So this would equal this value plus our step. And because we don't want to lose it, we'll put a $sign, oops, wrong place, put a $sign there, and scroll down until we get to 1. Should be 20 spaces. Now we got all the way to 1. F of x is equal to 2 times x squared. So this element squared. And again, scroll down to fill it up. And now we need to multiply that by dx. So this equals that value times our dx. Again, I don't want to scroll away from that, so I put a $sign, and I'll fill this up. And then my integral is equal to the sum of these values, which is 1.34. So now going back to the blackboard, we can say that this is equal to 1.34. So that's an approximation of this integral. So let's do another example. Let's use dx being equal to pi over 5 to estimate the integral from 0 to pi of sine of x with respect to x. Okay, so again, we need to calculate this. We're going to need, scrolling back up, right? We're going to need so we've got what dx is. We need to know what is our upper bound for our sum, how many sums are we adding, and we need to know what's the input for each of those summands. So working that out, we have that since pi over 5 has to be the length of the interval, which is from pi to 0, that's just the length of pi, divided by n, which tells us that n is equal to 5. So we're just using 5 steps, and our x sub i's will be 0 plus I times dx, which is I pi over 5. And so now we can calculate this out. So the integral from 0 to pi of sine of x dx will be approximately equal to the sum from I equals 1 to 5 of sine of I pi over 5 times pi over 5. Now, we couldn't even by hand calculate sine of pi over 5 since that's not a nice reference angle. So we have to use a calculator to estimate this value. So again, let's go back to our handy spreadsheet and we'll clear out our values here. Start afresh. So the length of our interval is pi. Our steps will be pi divided by 5. Our x values, well, the first one is 0 plus this. Then the next one will be that guy plus this element. Again, freeze that. So that's 1, 2, 3, 4, 5, which we can see we've ended at pi. F of x is equal to sine of this value. So we calculated sine of these values or estimates of that. And then this will equal f of x times our dx. Again, freezing that cell. And then our sum is of those cells, and it's approximately 1.9. So going back to our blackboard, we enter in that this is approximately 1.9. And in fact, once we get the fundamental theorem of calculus, we'll be able to find out that this is exactly 2, that the integral from 0 to pi of sine of x dx is equal to 2, but that will have to wait until the next video sessions. So that wraps up the introduction to the definite integral. Keep on your hard work and happy mathing. See you next time.